dropping traffic or packets are very expensive in the network of training big data centers. And that's why there are these requirements for reliable traffic is much, much higher. And the stakes are higher when you go between buildings and between data centers. Like the XAI that Elon Musk is building, this Colossus data center is supposed to have up to 550,000 GPUs in that data center. And all of them need to get connected. And the way that, because they work together as one computer, that's the whole thing. So it's really the largest distributed compute endeavor ever undertaken. Given the traditional key encryption mechanisms, they actually can be hacked. Once you have a quantum computer, you can hack those keys very quickly. So that's not a good thing.
Hey everyone, it's David Bombal back with a very special guest. Martin, welcome to the show.
Thank you very much, David. I'm happy to be here.
Martin, before we jump into the interview, I've heard that you're very technical, so perhaps you can give us a quick overview of your background.
Yeah, I grew up in Denmark and I was a network engineer, started out back then doing things like X25 and dial-up modems, way before that was cool.
Showing your age.
And then I worked at Intel. Then I started at a company called Broadcom where we built some switches and silicon. So I've done a lot of silicon work. Probably have about 20 years of silicon development experience. Most of it is as a manager. I try not to design stuff because that I don't think it will break. But I have a few patents as well in networking technology.
You're very humble. I believe it's 20 patents that you have, right?
Yeah, something like that. Yeah.
So in other words, you know what you're talking about, even though you're too humble. Sorry, go on.
There's one up here. This show.
I love that. So tell us one example of a patent that you've got.
Oh, there's a lot of cool ones. The one I like is where you overlay a communication channel on top of another communication channel to use unused bandwidth to have like a remote connection on top. That is one. But there's another one you may have heard of, blade servers. And connecting, switches and blade servers was one of the old patents that I had. So yeah, we did a lot of fun stuff.
Martin, a lot of people who watch the channel are younger, are interested in technology. Would you recommend, if you were talking to your younger self, to get into networking, get into the stuff today, or would you rather become an accountant or do something else?
I think networking is very cool, and I recommend just to figure out and understand that there's not magic. Data is moving across, and whether that's wireless or whether that's via satellite or it's via your network connection, there is some medium that moves the data. And then how do you then get from A to B, and how do you connect these large systems together? I think it's super cool. It is, if you like problems, debugging problems, because it's super, super difficult at times. It's like really, really good exercise for your brain to find networking problems. If you ever try to debug some esoteric DNS problem, you'll get a head scratch out of it. I love it. I think it's like puzzle, real-time games and playing puzzles.
I'm glad you mentioned DNS. It's always DNS. DNS is always the problem, right?
It's always the naming service or some other. By the way, it's always the network. That's rule number one. Whenever something goes wrong, it's always the network. And therefore, there's a concept in networking that says mean time to innocence. So this is how fast can you prove it's not the network? And then it goes back to the compute people or the application people that said, oh, well, we didn't change anything. Oh, well, maybe we did. So the networking is always the one that gets blamed. And it's very fun to then, get to the point where you can prove innocence.
I was looking at this announcement from Cisco, and it's insane. You got to tell us about this crazy, insane router, if you like, because the speeds are really interesting.
Yeah, I would do that. Maybe we should go in and say why is it important that things goes fast nowadays? And of course, it's all about AI.
Yep.
In the AI world, there's compute. I like to say that there's three things that matters in the world. It used to be a different three, but now it's a new three. It used to be compute, storage, and networking, but now it's different. Now it's compute, data, and networking. So those are the three things that matters in life. And when it comes to AI, it really truly is the data is what fuels the compute of the AI, and the networking is what allows these compute clusters to interconnect with each other, so you can have these very, very large model and they can function. So networking is incredibly important when it comes to AI, as important, I would argue, as the compute, like the NVIDIA and the AMD GPUs.
Yes, I'm glad you said that because, I mean, I think for a lot of people who aren't perhaps involved in the setting up of data centers for ChatGPT, and I'll just use that as an example, and various other AIs, they think of NVIDIA GPUs and they don't always think of the underlying infrastructure, right? So when you talk about data, are you talking about like storage somewhere and then the networks connecting that to the NVIDIA GPUs? Kind of give us a picture of how it fits together.
Yeah, of course, there is a storage element in this as well, but that's probably the least of the worries. Today, it's about these GPUs that there's no AI model or training model, very few, I would argue, that can live on just one GPU. You have to live on many. In fact, they live now, if so to speak, on tens of thousands and hundreds of thousands, right? Like the XAI that Elon Musk is building, this Colossus data center is supposed to have up to 550,000 GPUs in that data center. And all of them need to get connected. And the way that, because they work together as one computer, that's the whole thing. So it's really the largest distributed compute endeavor ever undertaken. And it keeps scaling. It has been scaling for a long time. And I think the way, if we break it down a little bit and talk about, well, how do we scale these things? If you start with scaling inside a box, and then you scale inside a rack, a compute rack, and when you do that, you use what we call scale up.
Yeah.
So that's what gets you inside the rack scalability, very, very high bandwidth. NVIDIA has something, they call it NVLink. Others have other ways to do it, maybe with Ethernet. Scale up Ethernet could be an example of that. So that's inside the rack. But as I said, it's not enough you have to scale between racks. And that's what we call scale out. And that's been what has been the traditional, the paradigm for scaling AI clusters for a long time. However, they keep growing. And now you can't fit inside a data center anymore. There's simply not enough room, power, space for these training clusters. So you need to scale them between data centers. And that's where we scale across. That is the technology that we use for that. Now, that's a little bit different. Each of these are a little bit different requirements. Like the scale up is very latency specific. It's small distances. You know exactly what's going on. Scale out is maybe inside a large data center, but is still within maybe a kilometer or a mile. That the distance you're limited to. And you have a lock on the door in each case, right? You don't have to worry nobody comes in and mess with it. When you go between buildings or between data centers and scale across, you now have different requirements. First is distance is longer. That has some networking complications to it. And also security is different. Now you need to have encryption. And importantly, which is in this new world, you have to scale a lot of bandwidth across in order to really scale two data centers to look like they're one.
So Martin, I'm a bit slow, right? So scale up is within a rack, and then you had scale out within a data center, but now the stuff's getting so big, like you said, with Elon Musk's AI as an example, that it can't fit within a single data center. So now what was the term again? You're scaling between data centers, right? Across, I think it was.
Across, yeah. I have an analogy that maybe, which might work. I think of it as scale up is like going between floors in your high rise or in Manhattan. And so the elevators move up and down really fast. You get from one floor to the other floor pretty fast. Okay, going between buildings, now you have to take the subway. But it's pretty good. You can take the subway. It moves pretty good. If one is not available, you take the next one. And now scaling across is like taking the train, the high-speed train. And now it becomes important because if, let's say, you come from far away from Florida into Manhattan or wherever it is, and there's it's congestion on the platform. You can't get out of the train. Well, you just spend 5 hours or 6 hours on a train and you can't get it. And in the case of training runs, those packets, if you think of the people are packets with information, if you miss out just a packet, or if you drop some of this on the floor, you have to restart the job. Now you have to go back to your checkpoint and restart your job. That maybe takes weeks or months to run. dropping traffic or packets are very expensive in the network of training big data centers, and that's why there are these requirements for reliable traffic is much higher, and the stakes are higher when you go between buildings and between data centers.
Okay, so you've teased me enough now, right? When I read this, it's a router or router from where I am. So you've got a router, not a switch. I'm assuming that's because it's between data centers. Is that correct? Because it does the encryption.
Sorry for interrupting. I think what's a router and what's a switch? Generically, I've been around this long time. The definition of a switch is essentially shallow buffers and limited packet processing capability, and for sure no built-in security measures of any kind. The router is the advanced guy that deals with the complex networking, and I would show deep buffers, lots of packet processing capabilities, and lots of security capabilities built in. And that is our definition. Now, what we have built at Cisco, we built an architecture that can do both, that's merging both into one. We call that Silicon One. And the system that we're talking about here is built around that architecture, and in particular built around one of our latest chip called P200.
So I hope you're going to show me that. Just before we get there, I've got an analogy. A lot of people at home might recognize this kind of stuff like 10 gig Ethernet or 1 gig Ethernet. That's what a lot of people have at home. And then like here, I've got 100 gig QSFP28. But you got to tell me, how fast is this router, and like what speed interfaces does it take and so forth?
Well, see, I would say here, I have an 800 gig.
Yeah. You're killing me there, man. Well done.
So 800 gig, if you think of that, that's a lot, right? That's 800 1 gig links. Imagine that 1 gig to your home. That's 800 of those running across this one. And our chip that we have is this one, and this is the P200, a very large silicon, and that can support 64 of these into one unit. So 64, wow, which is also known as, when you do the math, it's 51 terabit of data that we can switch and buffer and encrypt at line rate. So it's quite an achievement, and it helped us build larger networks, because it's actually not enough to connect these data centers together. Just one of these are not enough. And that's why we can put many of them together. In fact, we can scale it very, very, very high, up to 3 exabit. So 3 exabit. You know what that is, right? Of course.
No, you got to explain that to us, because not everyone. I'll know a lot of the answers, but not everyone knows what that means. So, the router is going at 51.2 terabits per second, because you got 64 of those 800 gigabits per second QSFPs in them, right? And then that's the chip that goes at the 3 exabits. Is that correct?
That's the building block that goes into our system that's called the 8223, which is the Cisco system. And now we can put a number of these systems together, a large number of them, and so many that you probably don't need to, but we could build an interconnect fabric that would give you 3 exabit, which is the same as 3,000 petabit. And then you say, well, what is a petabit? A petabit, in other terms, is 1,000,000 1 gigabit. Now, I'm not sure anybody will build it anytime soon, because you're really limited to how many fiber connections that you can have between a building, and 3,000 exabit is a lot.
So, Martin, I was looking at the announcement. One of the things that's mentioned here is security and something about quantum. So perhaps you can explain why that's important and why this has been implemented in the router.
The importance of security when you scale across and you go in long distances is that you really don't know what's happening with the traffic. So a fundamental requirement, you have to encrypt your traffic between the buildings. So we do that at line rate with techniques called IPsec and with MACsec. And so all traffic, as fast as the box goes, we can encrypt. But there's something called quantum computing that is, coming along. Maybe we don't know when, but it's a little bit scary for the security folks, because given the traditional key encryption mechanisms, they actually can be hacked. Once you have a quantum computer, you can hack those keys very quickly. So that's not a good thing. So there's something called post-quantum safe compute, or post-quantum encryption techniques. And we have already built the silicon that is ready for that. So once the protocols that resides on top and the software is ready for that, the machine that we have here can get upgraded to it. And it's not something that is quantum is still a little bit out there. We don't really have a very effective, usable quantum computers today because of many other things we can talk about.
Yeah, I mean, people are predicting 3 to 10 years, something like that. It might be here. So I'm really glad that this is already in the hardware. I mean, you shaking your head. I don't know when it's going to come, right? But it's coming.
The funny thing about quantum is it's all about error correction. So that's, you talk about how many qubits you have. And then so you need to have 1 million qubits to have something really, really strong. The problem is that you may need many more million qubits in order to have actual usable qubits because of this error correction stuff. I give you one fun quote that said, quantum is definitely gonna happen, and quantum computing is gonna happen, and we're gonna get to these big machines. There's just one problem with it. We don't have enough helium-3 on Earth to cool a 1 million unit qubit machine yet. But then again, we might be able to do some asteroid mining. But that's the scale we're talking about.
I love that. But I mean, so there's encryption between the data centers, but obviously the routers across all those links are encrypting data. It's quantum safe. One thing you didn't mention, and I think it's in this document somewhere, how far away can the data centers be? I think is it 1,000 kilometers, something like that?
Yeah, the reality that the data center can be very, very far away. And why do they want to be both? It's all comes, where is the power?
Yeah.
You have to stitch power together, and you can't get enough power. So that's why these data centers are moving to where there's more power available, hydropower, whatnot. And now, but they're still so big that you need to connect them together. So we connect them together with optics. It's a little bit similar to these ones, but they're called coherent optics that are meant for long haul. And they can go efficiently up to 1,000 kilometers, but we can do more than that. You can even go across the continent. That's what is going between Europe and the US. These long haul optics is what is needed, and the router needs to be ready for that and needs to be supportive of these long-haul optics or coherent optics.
But at those distances, isn't it going to cause problems for the AI? Isn't there delay, perhaps, or something like that, or is it not an issue?
No, the latency is a real thing, and the latency means a couple of different things. You can sort of hide latency when you transport. And in this case, is these things about transporting latency back and forth, where you send very massive amount of data, you can hide a little bit of that latency. As long as you don't drop the packets, that's where you get into trouble. But it's okay that the training clusters can manage that. Now, of course, they like it to have low latency as much as they can.
Yeah.
But that's why you want to be inside a rack. Well, you can't just be inside a rack. Well, I want to be inside a data center, so I have to, okay. At some point you say, well, I have to trade off. But then the real important thing about when you go between buildings and maybe they're 100 miles apart or 10 miles apart, you still need to encrypt all the traffic, and you need to have buffers that can manage these bursts so you don't drop traffic on the floor.
So that's a good point. I was looking at your slide deck that I was given, and there was this slide about deep buffers and shallow buffers. And can you explain why that's important, what in this scenario?
Yeah, I think the best way to think of it, it's sort of the shallow buffer is how much traffic can you absorb. It's almost like a conveyor belt of stuff that's coming at you all the time. If you have a very, very long conveyor belt, you can't stop it. You can only absorb as much as it comes in, and then you have to deliver it somewhere else. The shallow buffer means you have a small basket at the end of that conveyor belt, and when you overfill, you just spill it on the floor. And what is the distance? What is that to do with it? Well, latency is speed of light. So the longer you go, the more latency you have, and the more data you have in flight, meaning like your conveyor belt with stuff on it is in flight, but you can't stop this thing. So that's sort of a model to think about how many bytes or kilobytes or megabytes of traffic is in flight on the wire, from you start in one end to the other, and it's quite a bit.
So, I mean, in this example, I was reading it's a good idea to have these deep buffers, right? Because a lot of people would say short buffers in a switching environment or shallow buffers in a switching environment are better.
Yeah, shallow buffers in a switching environment is good. Deep buffers in a routing environment is required.
So I was looking in the announcement that the P200 silicon can support new protocols. Are there different kinds of protocols in a data center that like a traditional person perhaps at home or an enterprise won't know about or encounter?
There's a constant evolution in AI networking. In fact, it goes faster than ever. It is blistering fast, and part of it comes with new protocol that is getting introduction or new requirements. There are new protocols like scale-up Ethernet that is being introduced. There's a few other that are being introduced called ESUN as well. So these are all attempts to optimize the protocols that are needed to make the AI training networking better. And for what worked 20 years ago, it may not work today. So there are lots of changes. And the reason why our programmability that we have in our solution is so crucial to that is because if there's a new protocol requirement that comes our way, we can open up our little programming machine and change the program that runs inside our P200 machine. And there you have it, a new feature. If you don't have it, it'll take 2 years before you build a new chip, and then you have to get to market and so forth. So the velocity of innovation that is happening on networking and AI is really something that plays into a programmable architecture like ours.
What language are you programming it in?
It's a programming language is something, it's called P4. So it's a very specific language that are meant for networking, and that's sort of the way we define it. But yeah, look it up, P4.
Yeah, I mean, it's very interesting to get into the P4 stuff, but we don't have time for that. But I will mention this, right? The operating system running on these routers, I believe it's not traditional iOS that a lot of people may encounter.
In this case, we support quite a few different routers. We of course support our XR operating system, which is sort of our carrier grade that is intended for wide area network and data center interconnect. But we also support a new open source system called Sonic that traditionally has been used just inside data centers. It's open sourced. A lot of the hyperscaler use it. And now it's starting to find its way into the edge of the network and across scale out. And the reason for that is really about automation, that the hyperscalers, their networks are so highly automated so they can manage it with few people, that they need to have these fine-grained observability features and automation features built into their operating system, and they can change it themselves without having asked their vendors for changes.
And Sonic's open source, right?
Sonic's open source.
Yes, so you've got Cisco hardware running open source operating system, but you can run iOS XR if you want to.
Well, in fact, we offer this in even more. We also sell the chip as just a chip if somebody wants to build on this system. So we sell the individual built-in blocks, and then we put it together. And it's really about just meeting the hyperscalers where they are. We can't dictate how they want to do stuff. That it doesn't work that way anymore. But in many cases, they look to us to put the solution together.
The infrastructure is Ethernet, because you've mentioned the Ethernet between places. I'm assuming in the data center it's a bunch of Ethernet, or is it other technology that's physically used there?
I would say it's all Ethernet. It's all Ethernet today. There historically there's been some use of InfiniBand, which is its own little thing that we'll use to do the scale out between racks. I think the problem with InfiniBand is that it's quite good until the network gets too big, and then it can't really keep up with the scaling requirements like the hundreds of thousands of GPUs. So Ethernet has proven itself to be a technology and a standard that has adapted to requirements over the last 40 years, and I see no reason why that wouldn't continue that way.
And I'm assuming it's like fiber cables, right? Or is it copper, or is it a mix, or
inside the rack today it's copper. Copper is still cheaper than fiber, and it's if you can use copper, you should use copper. But between racks, it's fiber, and it's a form of fiber, single mode fiber that goes a couple of kilometers, and then between buildings or between regions, you have these coherent fiber connections as well.
So Martin, I was just looking at this PowerPoint again. You had an example with an 8804. Which was like a much bigger router. This new one is like 3U, I believe. So perhaps you can tell us about like the efficiencies. I'm assuming power you mentioned power in a data center, especially these AI data centers, is a major problem. And I'm assuming they're going to be happy that the thing uses less power, it's smaller, etc. So perhaps you can tell us about the innovations done there.
Yeah, lower power is always a good thing. It's cheaper, less heat is generated and so forth. But what we have done here is that we essentially comparing ourselves to the closest thing we could compare ourselves to is actually a modular system. So it's a modular system with line cards, 8804. And we are at least twice better in density, twice better in power. I think we're 65% less power. And that is by adding also in this encryption, line rate encryption. So in fact, if you look at where does that power reduction come from? It is because we're taking 92 chips. The old system required 92 data path chips, and we put that into one. So that is a huge saving in power and cost and complexity and cooling and so forth. So it's a massive engineering feat, and you will see that continue over time as we progress in the future.
Yeah, so let me ask you about that. Talking about the future, where do you see things going? Because it sounds like originally we had a rack, then you said it was a data center. Now it's multiple data centers being connected. I'm assuming it's just going to continue this innovation and the speed of, scaling up, scaling out, scaling across.
I don't see an end in sight. I mean, if unless something happens to the way that these training clusters, like the models changes dramatically, I think we'll continue to see more and more, speed innovation inside the rack, connecting the racks together and connecting data centers together, because the scalability of these training jobs, there's not a good end in sight of that. And I think once we got all this going, super intelligence here, now we still need to do meaningful workload with this, right? And that's also about data. Networking is key to everything about the AI revolution, because it's compute, it's data, and networking is moving the data. And that's just how it is. And it has to be secure, has to be reliable, and it has to be efficient.
I'm glad you said that, because for a while networking wasn't cool, but AI has really made it cool again. Networking is just going into a new dimension, it seems.
It is. And think of it like this. If you spend $10 or $50 billion on your new shiny data center with NVIDIA GPUs, you don't want it to sit idle because your network is not optimal or is not, you can't get the right product.
This router has 64 ports of 800 gig, I believe. When are we getting faster speeds than 800? Because 400 wasn't that long ago. Now we've got 800. Are we seeing anything developing towards higher speeds than 800 for a fiber?
There's initiative to 1.6. And that probably will start inside the data center first, inside the rack, go faster, because the fiber connections and the optics that goes coherent optics it takes a little bit longer to go faster. So for the foreseeable future, we'll just see a bunch of 800 gig links that are connecting data centers together, and then you put just a few thousand next to each other of those, and then you send traffic across, scale across, going faster. Probably in a couple of years.
Martin, thanks so much for sharing. Sorry we're out of time. Really appreciate it.
I appreciate it. Thank you so much.